Hello and welcome. So today's lecture, we're really going to kick off the structural mechanics aspect of the course, and it's going to really start with this section on what are the properties of plane sections and how to find them. But before we get into how we determine what a plane section is and how do we define the properties of it, we should really find out, well, what is a plane section? So if we look at the member that I have drawn here, you can think of a plane section as really any slice that cuts through this member. And, I've drawn it here and it really goes out, to infinity. But we tend to think about it just in terms of the bounds of the cross section and the exterior of that cross section. And so it's really just a plane which is cut through a member which is, orthogonal, so perpendicular to the length. And when we say a plane, think like an XY plane, so like I have drawn here. So, why do we use these plane sections? And it's really because if we determine some properties of these, down the line we can determine what is the bending stress which this member is subjected to, or its deflections. And there's some nice mathematical relationships which come from just these plane sections. And so, like I say here, we use them because we have some good analysis tools which are tied to them, which work really well when we have these long, sort of skinny beams. So if we have a length of a beam over its depth, that aspect ratio greater than 10. And really this is, this plane section stuff, which we will start getting into here shortly, will work if we're a little bit outside of this range, as long as our shear deformations are quite small. And so this sort of caveat here is going to be more important in a future lecture when we do a derivation of bending stress, but it's always good to sort of have, where these plane sections properties are going to hold true right at the start. So, and again, we've sort of talked around a little bit of what a plane section is, and that we know they're somewhat useful, but how do we use it and why do we use it? And it's really because we need some method to go from geometry to to a demand on a structure. So if we've determined what our external forces and moments are, we want to know that the internal stresses of a given cross section are going to be able to handle that. And so make sure that we're not going to overly strain the material, not overly deflect the material, and then not rupture or crush it due to our bending stress. And we kind of know how to do this for, say, an axial problem. So if you've got some length of a tube, it's got some length some length L and some area A. We put it under some axial stress. Well, we can work out what the axial stress is. It's just going to be that axial load divided by the area. And if we want to know how much it stretches, it's just going to be the axial load times the length divided by the area times the modulus of elasticity. And so for our cross-sectional property that we care about for axial problems is what we really want to know with these plane sections is what's our analogous property so that we can get to the same sort of thing around deflections and stresses when we subject an element to bending. And that's what we're going to start on today. Really, how do we get the equivalent, area or some analogous property to area for bending problems like we have for these axial problems? So to do that, we'll actually start with a little bit of review, and we'll look at moments of area. So those of you who've taken statics, you'll have come across the concept of a centroid, and really this sort of first moment area. So if you think about a first moment area, we have our generic engineering blob here. And in order to find it, really what we want to do is we think about some little area, discrete area, with dA on the blob, and we want to find out, what's its, moment arm distance to some point which will balance everything out. So if we think about this in terms of center of mass, really what we're doing is we're trying to find the location somewhere on this cross section where every little point dA will be balanced out. from all other locations. And so you can think of this analogous to like if you have a seesaw. So say you have a seesaw here, and we'll just say that it's got, some load 2p here and some load p there. Well, the distance of the fulcrum, which would be analogous to our center of mass, has to be located such that, everything's going to be in balance and we're not going to move around. And that's, again, somewhat of a review. You all should have already taken, first moment area, and this should be a bit of a review. But again, it's a good jumping off point here. So effectively, centroid is just the area about which this little block is going to be balanced by every other little block and its distance away. And this is why we call it a moment of area, is you think of this little block, if it's got some weight to it, well, there'll be a tiny force coming in and out of the page, and that force times some distance will be a moment. And much like with our seesaw, we've got some force times some distance. There's a moment going this way, and there's a moment going this way with this force times this distance. So you'd have 2p times L over 2, and you have p times L. And all of this will equal out just like that. And so if we want to write this sort of explicitly, the first moment area of this section here is really just, the sum of all of these tiny little squares, dA, multiplied by their perpendicular distance to some point which balances them all out. And so if we're writing all of that down, we would have our first moment area equal to qx is just going to be the integral over the area of this shape multiplied by, the distance y and every little bit of dA. So this is just the calculus which just describes doing this over and over again over the whole area of taking the area multiplied by some distance and the area multiplied by some distance. And we can do this either about the x-axis or about the y-axis. And, much like with I said on the seesaw bit, the centroid is just the point where if you concentrate all the load, you've got the same moment area about all axes. And that's really, the same as the balance point there. And that means that everything is all balanced out. So, if we do that, well, we can write out what our first moment area is explicitly about both axes. And so if we take, this is effectively, we're summing all of our area, times some distance away. We'll do it about the x-axis first. So if qx equals the sum of the area times y dA, we will have the sum of the area y dA equals the total area times its centroid about the y-axis. We'll do a little bit of algebra and rearranging, and that'll give us y bar equals the integral over the total area of y dA over a, so I'm just effectively moving the area over there and then just flopping the two equations. And then that means that we can solve all of this out where y bar equals qx over a equals y dA over the area. Remember that sum of the area dA equals the area. dA, and of course we could simplify this down to the sum of yi ai over the sum of ai. And similarly, if we're looking about the centroid in the x direction, first moment area about the y-axis is just going to be the integral over a x dA equals a x bar. Rearranging x bar equals sum of a x dA over a. So x bar equals qy over a equals y x bar dA over integral dA. And of course this simplifies to the sum of each little area multiplied by its distance to the centroid over the sum of the areas. So hopefully you have seen this derivation before and it's nothing new, but the points which I want to sort of bring up is the fact that with each of these little pieces, all we're doing is just looking at, well, effectively, each of the little areas, what's its sort of contribution. So you think about this analogous to force times a distance, and that's the moment about this distance. And then really, if we come around the centroid, lots of stuff sort of cancels out, and it's really effectively the balance point for all of our forces. So that's the first moment area. Now, if we look at the second moment of area, where we're doing much the same thing, and this is really our first property of plane sections that we care about, and it's what we call second moment of area or moment of inertia. And it's really, how resistant to bending a particular shape is about a given axis. So the moment of inertia about the x-axis is how much bending resistance something has about the x-axis through a given point. And so that should make some sense to you if you're familiar with physics, where inertia is how much effort it takes to move something or to stop it. It's much the same here. That's why we call it moment of inertia. So if we're looking at, again, our same blob, and we're going to look around, say, bending about our centroid and about the x-axis here. So x, y. Well, we know that the first moment of area is simply going to equal y times dA over the area, which is, obviously what we just found right here. Yeah, it's just going to be first moment of area, sum of over the integral over the entire area of y times dA. So that's every little piece, dA, multiplied by its perpendicular distance. Now, our second moment of area well, you can think about if the first moment of area is just this little area multiplied its distance, and hence the moment. Second moment area is effectively taking this whole thing, and we're multiplying by its distance again. So we get effectively y times y dA, which is just going to simply be y times y dA equals y squared dA. So effectively all we're looking at is, we're taking kind of our centroid and we're just multiplying by the perpendicular distance again. And then that gives us an indication of how much effort it takes to rotate this section about a given axis. And if we were to work this out for the centroidal axes, we would have Ixx is going to equal the area of y squared dA, and Iyy is going to equal So yy is going through the axis turning about the y direction, is the integral over the entire area of x squared dA. And then just a thing to note, that the integral over the entire area is the same as the integral over the x and then the integral over the y. So that's our general formulation of it, and that's sort of the math heavy part. But let's work out how to use this. And let's just do it by applying it to a simple equation here, where we have just a simple rectangle. Find the moment of inertia about the centroidal axes in both the x direction and the y direction. So we have this rectangle. It has some width b and some depth d. So let's just tuck right into this. If we do the ixx is going to be equal to, we'll go x, y, because that's the same as the going over the area, times y squared dx times dy. In fact, we'll put up here, just so we're clear, this is simply the same as a y squared dA. All right, so we really just want to work through a definite integral. So over the x, we want to integrate over the entire distance, some distance from the centroid, minus b over 2 and plus b over 2. And then when we go about the y direction, we're coming about the centroid, we want to go up some d over 2 and then minus d over 2. So it's simply going to be equal to b over 2 minus b over 2, and then integral of d over 2 minus d over 2 times y squared dx dy. Well, definite integral, if we're just, we can pull this out. We have a constant, and then we can sort of work this out. Well, the integral of dx times from b over 2 to b over 2 is simply just going to be the width b. You can think of that same as the sort of area there. So we get d over 2 minus d over 2 times y squared times b dy. And then if we work out the definite integral of this, we would get, so we'll integrate, we would end up with our constant b times y to the third over 3. And we will evaluate that over d over 2 and negative d over 2. And this would, we can expand that out, and this would give us b times d cubed over 3 times 8. So that's just simply d cubed and 2 cubed. Plus plus, since we're subtracting a minus. b d cubed over 3 times 8. If we simplify this all out, we end up with b d cubed over 12. So ixx is going to equal bd cubed over 12. And really what this is doing is we are effectively looking at, if we have some area and we have some distance here, we're taking a strip that has the area equal to the width times a height dy, and we're working out what its second moment area is of y squared. And that's all what this equation is showing. And we're going to do that all the way up and all the way down from the x-axis. And if we do that, we work out that we have this moment of inertia, bd cubed over 12. All right, so let's also just work out what we would have if we looked at the y-axis. So similarly, we can rotate this direction. There's nothing to say we can't rotate an element in the other direction. So if we go I, y, y, is simply going to equal a x squared dA, and that's again just our definition of what our moment of inertia is about the centroidal y-axis. And so that's going to give us equal to b over 2 minus b over 2 times d over 2 minus d over 2, and this is simply definite integral across the x-axis, and this is the definite integral across the y-axis, and then multiplied by x squared dx dy. Similarly to the x direction, our dy, we'll find out that we end up with, if we take out this integral here, we end up with b over 2 minus b over 2 times x squared times d times dx. And then we can create our definite integral here. We'll integrate, we'll end up with x to the third over 3 times d. And then we can evaluate that over b over 2 to minus b over 2. And that will give us d times b cubed over 3 times 2 cubed minus negative d over b cubed over 3 times 2 cubed plus plus, and then that'll give us d b cubed over 12. So just like we had in the about the x direction, we get the same thing, except for our widths and our depths are changed. And this is one of those very important equations. And one of the few things I would tell you to memorize is that the I for a rectangle equals b d cubed over 12, where it's about the centroidal axis, you have the width, and you have the depth. So we'll find out that this is a very, very important equation that we'll use again and again and again. So that's for the moment inertia of a rectangle. So what about if we've got, a bit more complex shape? Like, not everything we work with in structural engineering is a rectangle. And so, just like if we're working out centroids, and we're trying to work out the areas of a centroid, we can, add and subtract each little component to then get the sum of, what our area in that centroidal area is. And we can do the same thing with moment of inertia. But we're only going to start with this very special case where each of the little components has a common centroidal axis. So if we have that, then our moment of inertia for the x and the y direction total, it's just going to be the sum of each of these little ones. And so we'll start with this sort of simple structure here where it's just effectively a rectangle with a rectangular hole in it. And we want to find both the moment of inertia in the x and the moment of inertia in the y direction. So we can quite simply just work out, I x x total is going to equal ix of the whole thing minus ix of the whole. So sorry for the vernacular there, but ix of the outside minus ix of the inside. So if the moment of inertia of a rectangle is just simply bd cubed over 12, we can apply it this way. So we will have equals 1/12 times bd cubed minus 1/12 bd cubed of the whole and the whole. So working this out, 1/12 of the outside, the width is going to be 50 millimeters multiplied by, we have a depth of 50 plus 20 plus 20 is 90, 90 cubed, and then we're going to minus 1/12 of the width of this hole, which is 50 minus 10, which is equal to 30. And then this distance here of the hole is 50 cubed. And if we work that out, Ixx equals 2,725,000 millimeters to the fourth, which is the same as 2.73 times 10 to the sixth millimeters to the fourth. Now, if we want to work out the y direction, again, it's much the same. Iyy equals Iy whole minus Iy whole. Iyy equals 1/12 times, our width now is 90, multiplied by 50 to the third, because we're bending about this direction, and this, remember, the d is always going to be the direction about which you bend, minus 1/12 times 50, width minus times 30 cubed, and that is simply going to be 825,000 millimeters to the fourth. So Iyy equals 8.25 times 10 to the fifth millimeters to the fourth. So there we go. So just a few very simple examples of how to calculate some properties of plane sections. And again, this is really just sort of the beginning of how we we'll utilize these plane sections, and it's this moment of inertia, which is going to become the workhorse of your analytical work for structural mechanics, and it's really around this moment of inertia. For a rectangle is a common one. There's also the use of circles and triangles, and we've worked out how to do these complex shapes, but only if all the complex shapes share a common centroidal axis. If this axis was somewhere else, or if the shape was non-symmetric, what we did here would not work, and we'll learn that how to deal with that in a coming video. But with that, that's our introduction to properties of plane sections and moment of inertia, particularly this second moment area. And as I said, we will be able to use this in conjunction with some other mathematics to be able to determine what the stress is across the section, or what the deflection is. So with that, thanks for watching.